Hi, my name is Matthew Guzdial, and I hail from the Entertainment Intelligence Lab out of Georgia Tech. I'll be presenting this talk entitled Toward Machine Learning-Based Creative Automated Game Design. That's a lot, but the question we're interested in is what if we could add games together? So we can imagine any mashup here. For example, Mega Man, there on the left, its original North American NES cover art, and Super Mario Brothers, there on the right, with its original NES Japanese cover art. What would happen if we could mash these games together to create new games in the sort of space around them or between them? Well, one of the things we could do is we could empower novices to make games. Speaking to novices or people who would like to make games, they often talk about the games they'd like to make in terms of this sort of mashup. Since games are sort of a simplification of reality, or at least can be understood in that way, we can imagine technical results that we learn from this applying to other domains. In addition, game design represents an opportunity for creativity research, as noted by Liepis et al. In 2014. So, by empowered novices, what I mean is that many of the people who would most benefit from the ability to make games lack the resources or the ability to pay for someone or for themselves to make games. For example, you can imagine educational games, games to inform or to persuade, or human computation games. For example, a recent human computation game, Play to Cure Genes in Space, which was created by a game studio financed by some cancer researchers. But not everybody has that ability, and think of all the good we could do if more people could have access to the ability to make games. In terms of games as a simplified version of reality, this has actually been a common through line in automated game playing research. In this case on screen, you're looking at Google's DeepMind playing through some Atari levels or training on some Atari levels. And the idea here is that by learning to play more and more complex games, eventually we can get techniques that we can apply to reality, or at least limited pieces of it. And this research can be understood as in parallel to that. In terms of creativity research, there's actually been a long focus on artificial creativity in academia, and more recently it's gained more mainstream interest. I think that the crowd here is probably pretty aware of this. In terms of creativity in games, though, it has to follow some different constraints. Games are dynamic, they're interactive, they have to follow consistent rules, and this is interesting in terms of applying creativity to this. In addition, games are popular, which is great in terms of both spreading the word about research and getting that out to the public, and also it's helpful as there are many people who are qualified to play and test creative games. So there's a question of how we would actually do this thing. So we could look at how humans do this, at least at a high level. So the idea is that humans take some expert knowledge and some creativity, some ability to recombine that knowledge, and they work for a long time on a PC, often with some cool hair, and eventually you get a game out of that, a game you can play. So how do we actually cope with the lack of expert knowledge in this case, if we want to use the same process? We could encode it. So for procedural content generation, as used in No Man's Sky from Hello Games in 2016, there's a lot of encoding of design information in terms of rules and heuristics and grammars, but that's difficult. It's time-consuming. So alternatively, we could try learning it. So here's the process. Here's the pitch. The idea is that we're going to go from some game engine that we never see. We're never going to have direct access to it. We're instead going to look at the output of that game engine in terms of gameplay video of somebody playing that game. And from that, we're going to derive a learned level design model and a learned game engine, which hopefully is identical to the original game engine. So you might ask yourself at this point, why not just learn directly from the game engine? It's a good question. One of the reasons is there's a lot of video online, a lot of video of people playing games. So there's a big corpus that we can just access right now. There's other benefits as well, though. For example, the ground truth engine is not always going to be accessible. For newer games, it definitely won't be. For older games, it might be, but there's some legal issues involved. And if we want to move on to something like reality, well, in reality, I can't actually access the raw memory of a scene in reality. In terms of containing the player's reaction to game elements, video is also really helpful, as it can allow us to sort of derive some semantic meaning of game elements from the way that the player reacts to them. Lastly, video is general to many different domains. Many domains can be expressed in terms of pixels over time. Okay, so hopefully that alleviates some questions you might have. Let's take a look at this sort of learned level design piece here. So there's actually been a lot of work in terms of learning level design. In particular, we have Sam Snodgrass and Adam Somerville doing some great work. Both of them will be or have given talks at ASYNC already. So I'm not going to go too deep into the level design here. I'm just going to hope that you trust me that you can actually learn level design. The approach that we use is actually something we adapted from SIGGRAPH, some work on modeling shapes or 3D models based on the sort of probabilistic model of components. The idea in general is that we're going to go from some gameplay video, we're going to use OpenCV, which is this open vision toolkit, to be able to parse each frame of that video, and to that extract for each frame what components are where, with what width and height, and with what confidence that they're actually there. From that, we use some automated clustering to be able to drive this probabilistic graphical model, sort of probabilities over shapes and the relationships to one another, which we can use to both evaluate and generate out level sections, which we can string together to make new levels. If you're interested in this, you can check out game level generation from gameplay videos for more info. So we can do that. We can do this one. We can learn level design. Cool. What about learning game engines? There's been some work towards this, but it's less common. So we're going to dive a little bit deeper in terms of the technical details here. So we're going to go through a system overview, but notably, this is still going to be fairly high level. If you'd like more information, you can check out Game Engine Learning from video. So the system overview in this case, we're going to start with choosing a game. We're going to use Super Mario Brothers. It's popular and well-known, so why not? The first thing that we need to do is we need to parse video of the game to extract facts for each frame. Now this is similar to what we did before, but in this case we're going to need some hand-authored facts to give us notion of what's actually happening, to structure the information a little bit more. We're then going to scan through the sequence of frames, now represented as sets of facts, and when we cannot correctly predict the next frame, we're going to run something that we're calling engine search. I should note at this point that we're defining an engine, game engine, as a set of rules, where each rule is defined by a condition, which is a list of facts that must be true for the rule to fire, and an effect, which replaces fact A with fact B. So the first thing, again, that we do is parse video. This is exactly the same as for learning level design. We get a notion of the components and their placement in each frame, in the scene, their width and height, the confidence that we have that they're actually there. However, we're then going to transfer these into sort of percepts, these different individual facts. So in terms of animation, we have a notion of what animation state something is on. In terms of spatial facts, we have a notion of where it's located on screen. Relationship X and Y is the relationship in terms of the distance between things. Velocity X and Y, in this case, is fairly straightforward, the speed at which things are moving. And camera X is the location of the camera in the world. So now that we have these things, we go through each frame, and for each frame, we're going to pass our engine the frame and predict what the next frame should look like according to the current engine. Now, the engine starts with nothing, so it's just going to predict the input if it has nothing. We can then compare the predicted frame with the actual output frame to get a notion of how far off we are. In this case, if we're off at all, we're going to go ahead and run engine search. Engine search can be understood as a modification or an extension of greedy search. What we're going to do is we're going to create children of the current engine by creating every relevant transformation for the specific frame of that engine. We're going to add every possible rule. We're going to modify every existing rule in the engine. We're going to delete every existing rule in the engine. One of these each for each child. We're not going to do all of them, or you'd end up with an ND engine again. We're going to then select the next current engine according to performance and parsimony. Parsimony in this case meaning how simple it is. So we want the basic simplest explanation for the transition. We're going to repeat this process until the difference between the predicted and true frame is beneath some theta. In this case, no difference. And notably, after each successful engine search, we're going to start our frame scan again all the way at the beginning. This ensures that we didn't break any earlier transitions. Okay, so I'm not going to go through our full evaluations here, but to give you a sense, we tend to do pretty well in terms of the physics, the jumps. You can see here the jumps of the character, the movement of the enemies. What we tend to not do so well on is the sort of flickering, the sort of animation states that things are in. In case you couldn't tell, the left here is output from the game engines, the learn game engines. The right here is the ground truth video. So game engine was passed the sort of previous frame and asked to predict the current one, and this is just truth here on the right. So going ahead and moving on, you might be saying at this point, hold on, Matthew, you said there'd be some creativity in here. And there will be, though I will say that I think that learning is very important for creativity. If we note that in our original pitch, we said that humans take their expert knowledge and they recombine it to create new things with their creativity. So what we're sort of after here, if we can take apart our learn level design, our learn game engine from this process, we can imagine other learn level designs and other learn game engines gotten from the same process. And in this case, it's Mega Man here on the left and Super Mario Brothers here on the right. And we need to somehow smush them together. So what we're really asking is, how do we get new models from existing machine learned models? And there's actually lots of ways to do this, but most of them aren't going to function particularly well when we have small input or training sets. And even if we could get them to work, many of these approaches are going to not really give us creative output. Imagine lots of machine learning methods which learn a distribution might just give us the average of the two games, and that's sort of boring. Instead, what we're going to do is we're going to use computational creativity. In particular, we're going to use something called combinatorial creativity, which looks at combining different pieces of two input sets to create novel output sets. These are techniques like concept blending, amalgams, or case-based reasoning adaptation methods. In particular, I've actually done concept blending for level design already, which is nice. That's one piece of this at least. I'm going to go through this fairly high level again. You can check out Learning to Blend Computer Game Levels if you're really interested. I know this figure is intense. We're going to break it apart piece by piece. So what we do is we have these sort of extractions of different pieces of our learned level design model. In this case, a sort of overworld level, and in this case, a castle or boss level. We're also using a asymmetrical concept blending or metaphorical concept blending, so we have a source and a target. So going from here, as these two things are input, we also need as input a set of our final desired components at the end, a graph that can explain relationships between these things. So what we do is we construct a mapping from each element of the source to each element of the target, using, in this case, their relationships to one another. So it's fairly generic to what's actually in these individual boxes. From that, we're going to collect the mappings that actually allow us to fit that final set of desired components based on how closely the mappings are to one another. From that, we're going to construct a sort of blended version of these graphs. And from there, we can put this back into our probabilistic graphical framework and use that to generate out or evaluate new blended sections of level design. And in terms of output, you can get all kinds of cool stuff. You can get, for example, these top two here are the system's attempt to replicate some human blends. And on the bottom there is this brand new thing the system came up with, this sort of castle, underwater castle level. So you might ask yourself at this point, what's left to do? Well, I've already shown that we can do level design blending. So the naive thing is to say, well, you can just blend some game engines and we're done, right? Well, not quite. There's lots of things I haven't touched on here. Things like semantic meaning and narrative, game audio, gameplay visuals that are important to the game experience as a whole. And that is sort of the reason for this title. It's not just machine learning-based creative automated game design. That toward is really important. That's doing a lot of work right here. But I would say, even though we're not there yet, we're definitely the closest we've ever been. So I'd like to say a brief thanks at this point to my advisor, Mark Riddell, and the rest of the Entertainment Intelligence Lab, and thanks to the National Science Foundation for supporting this work. If you have any questions, there will be a period, I think, directly after this, but if you're catching it later, feel free to email me at mguzdial3@gottech.edu, or you can always tweet at me. Hit me up on Twitter. I don't tweet at you. You can always tweet at me at Matthew Guz on Twitter. Thanks so much. Bye.